Perfect. So we'll start our discussion or continue our discussion on fluid statics as we were doing in the previous lecture. In fact, let me quickly recap the previous lecture's contents, and then I'll continue from there. So let me open the previous lecture notes. So in the previous lecture, I started with what fluid statics is, and I mentioned that it is important to know about the information of the pressure field in statics because that is the only field that is of interest. I talked about a couple of applications, and then I also mentioned briefly that pressure also exists in moving fluids, not just static fluids. But in this chapter, in this discussion, we are only interested in static fluids. Then we moved on to the discussion on finding out the relationship between the spatial pressure gradients and the forces acting on a given fluid element because of those pressure gradients. Because we know that spatial gradients in pressure create forces. So we started with an element, and this element had a size of delta x, delta y, delta z. So this was delta x, this was delta y, and then we had delta z. And then we wrote the expression for the x velocity, which is the one which is acting on the left hand side on the plane x equals, well, let's call it x. So this is fx, and on the plane which is on the right hand side, the force is f of x plus delta x, because the right hand side plane is at a distance of delta x from the left plane. And using Taylor series, we were able to write the expression for f of x plus delta x in terms of the pressure values at location x. And we stopped there, so I'll continue from here. So let me copy this content into the lecture for today. Seems like I can't do it. No problem. So I'll quickly draw the figure again. Okay, so this was our cube element. Let me confirm what the axis we had taken. Oops. Sorry, I think I deleted that. Anyways, I think this delta x was whatever we have drawn. And then delta z was taken as this one. So then in that case, well, this should be delta y. No, this was delta x. Right. So f of x was the pressure value P and uh, times delta y delta z. So pressure times area on that infinitesimal plane, and then f of x plus delta x was oh, sorry, there was a minus sign here that I missed. Well, no, this was positive because it's acting in the positive x direction, and f of x plus delta x has a minus sign, and then we have p plus del p by del x times delta x, and then you have the area, which is delta y delta z. All right, so if you take the difference between the two, because the net force acting on the element in the x direction is the difference of the two, so that difference comes out to be, which we call delta fx, which is f of x plus delta x minus fx, or you can simply add them because in this case we have taken care of the direction. Okay. Strictly we do a minus sign because we use the same sign, but here I have taken care of the directions. So what you'll see is we end up getting minus del p by del x, and then we have delta x, delta y, delta z. So the net force is simply because of the difference in pressure between um, uh, the x plane and the x plus delta x plane. Right. And if I do the same thing in the other two directions as well, so if I do it in the delta y direction and the delta z direction, I will end up getting similar relations. So let me write the total force on this differential element. So this will be minus del p by del x along I cap plus del p by del y along j, and then you have delta x, delta y, delta z, which I'll call delta omega. Okay, so delta omega is the overall volume of this infinitesimal element. In fact, it's more common to write the ratio of the infinitesimal force to the infinitesimal volume, which we will call the force per unit volume. And so the volume size was our choice. So it's worth talking about the force per unit volume. So this becomes, and remember this quantity that you have, del p by del x I plus del p by del y j plus del p by del z k, is nothing but the gradient of pressure. All right, so this pressure gradient creates a force on this infinitesimal liquid volume. So this liquid is this liquid volume is a volume that we had considered inside the liquid. Now remember this force is because of the pressure gradient. So this is force per unit volume. We'll call due to pressure gradient. Any questions on this?
Sir,
Yes, sir.
we are taking the cube to be small enough so that the pressure doesn't vary along uh, the the faces, right?
Yes, you're right.
Okay.
So it's a very valid question that the cube is small enough so that when I go in the delta x direction, the planes we considered, the x planes, the pressure does not vary in the y or z direction on that plane. It's a very small cube. Okay, so I should have actually written a limit delta omega tending to 0. That is how we strictly should write it. Okay, in fact, I already had used dou, so we even could have written a df here. That could also have worked. But I mean, the ideas are, I think, clear. Any other questions? Right. So let's move on. I mean, there is nothing new here. You have learned about these ideas in the past as well. Just confirming again, you understand the meaning of a gradient. Is that right?
Yes, sir.
Thank you. So let us do a quick recap on the gradient because we'll be using that. So let me give you a question to think. If we have a pressure distribution, so if I draw the constant pressure lines and they are concentric, okay, these are also called isobars, constant pressure lines. And in this case, P1 is less than P2 is less than P3. So as you go out from the center, the pressure increases. So can you think about what the direction of grad P, or in fact minus grad P, will be? So it's a question. I mean, you can answer it if you want. So let's make you uncomfortable. Let me ask you, because it's very important we understand these ideas to be able to succeed in this course. So if the ideas are not clear, we'll have to go for a revision. So Ayush Sharma, do you want to comment on this? Do you remember, have you done much work with the gradient operator? That's okay. You can type if you want. What about Divyam? Is the meaning of gradient operator clear here?
Yes, sir.
So can you comment in the direction of the gradient of P?
I think towards the center of the circle, concentric circle.
Right, right. So, well, minus grad P will be towards center. That
Yes.
is right. Thank you. So in case you still don't remember these ideas, I will definitely recommend that you go and revise these things. And in case there is confusion as to where to revise these, you can always get back to me, and I can direct you to some material, a very good material on vector calculus. Okay, so minus grad P is towards the center because grad P is radially outwards. Pressure is increasing, and the radial direction is also from inside to the outside. So grad P will be radially outwards, but minus grad P is radially inwards. Okay, so we have learned this idea that the gradient is perpendicular to the constant pressure lines, or in whatever is constant we're talking about. Great. So let us move on. Now the example we took of this hypothetical fluid element in the previous slide, that hypothetical fluid element was stationary. Okay, but there is some pressure, there is some force because of the pressure differential. So how is the cube stationary? So there has to be some other force that is balancing that force. Otherwise, the fluid will want to move because of this differential pressure element, or differential spatial forces. So let us do a net force equilibrium balance, or for force equilibrium analysis. So the net force has to be 0 because the fluid is static, the 0 vector. So that means in this case we have a pressure force, as we just figured out, and we also know that in this case we have a gravity force. So I'll call it delta F gravity. I'm putting a delta because it's on a small element. Okay, so the delta F pressure, as we just found out, is minus grad P, and since we're talking about the force now, so we have to multiply it with the infinitesimal volume, and gravity is nothing but mass times a force of gravity is nothing but mg, and the mass of this infinitesimal element is density times its volume, and then we have the g vector. So this gives us that grad P in this case is equal to rho g. All right, so let's continue with this. So if we are dealing with water, so if we are working, let's say, with liquids, so in that case, well, shouldn't say before that, if that's okay. So we are under the Earth's gravitational field. We talked about that. So if we're working with liquids, then we know that the density is constant, or it's constant over a large or huge range. So whenever if we are integrating, we can take the density out from that integration. So let's expand this first. So we have g being given as minus g along k cap, or g along minus k cap. So let's say this is your so this was your k hat direction, then g is going downwards, so g can be written as this. So what that means is your del p by del x and del p by del y are both zeros, because this minus g k hat has to be equal to the left hand side. So the left hand side the x and y components, you can see if you add them, they will be 0 because there's no I or j components on the right hand side. So what that gives us is that del p by del z is minus G. In fact, I can write dP by dz because I already know that pressure is not a function of x or y from this condition. So this, well, did I miss a row? Yeah. So this, when I integrate, gives me let me do a minus rho, and G is also a constant, and then we have dz. So integrate from z1 to z2. So this is my z1 and this is my z2, and I have P2 pressure here and P1 here. So this integral is P1 to P2. So that gives me P2 being equal to P1 minus rho G, and then you have Z2 minus Z1. All right. I can also call Z2 minus Z1 as delta Z. This can be written, and then you can see that P2 is less than P1, which of course we already know that P1 is more than P2. So we can also write it the other way around. P1 is P2 plus rho G delta Z. Nothing new here. Okay, just ensuring that whatever ideas we knew earlier are still satisfied. Any questions? Okay, so let us move on. Now in this Earth's gravitational field, if I had to draw the isobars, since I know that the gravity is in this direction, then the pressure isobars have to be perpendicular to this, because the direction of gravity is the same as the direction of minus grad P. So I will get my isobars in this direction. And of course, the pressure is increasing downwards. So I'll write it as P1, P2, P3, and so on. Okay, so there is a question for you. I'll call it, well, let's call it FFT. It's not fast Fourier transform, it's food for thought. So if I have a glass and there is some water in it, then we know that the free surface, which is the one that separates the liquid from air, will be horizontal. So my direction of gravity is this. Now if I tilt the glass, and then I try to figure out what the free surface looks like, it will look something like this. Again, you'll see that it will be perpendicular to gravity. The question is, why is the free surface perpendicular to gravity? Okay, it's very intuitive, but I would still want you to, the ideas that we have just learned, to be able to apply that and show this. Right. So allow me to continue. And remember this chapter, there's nothing very new that we are learning here. We're simply mostly recalling, writing a formal relation in terms of pressure gradient and forces, but there is nothing new that we are learning. So this is the most rudimentary kind of fluid mechanics that we'll study in this um, discussion, in this chapter, in this course. Sorry. Now, if you were dealing with gases, then the density is cannot be considered constant. I mean, it changes a lot. So this relation that we had of dp by dz being equal to minus rho g. So we're still working under the effect of the Earth's gravitational field. So the force that is acting on the body is still gravity along minus k cap. But the density is not constant. So you have to use some sort of a gas law to write this density in terms of pressure. Okay, so you can write this as P upon RT. Then I can move the pressure on the left hand side. And if I do that, I'll simply write the final expression. I'll let you fill in. So my P2 is P1 times exponential times this. So still we have Z1, Z2, then we have P1, P2. Okay, so there's an exponentially decaying pressure as you go up. So if delta Z is 0, then e to the 0 is 1, so P2 is P1, which makes sense. But as you go further up from P1, then you will see that P2 will um, will decrease. Okay. Right. So in this case, we have assumed that the temperature does not change with Z. There's not much change of a temperature. So if you're working on small scales of let's say between different floors of a building and trying to see the pressure variation, then this relation can be quite good. But if you're working on the scale of the size of the atmosphere or some ratio of that, then you will have to take care of the change in temperature with Z. So I will say if large delta Z, then you have to use the temperature variation as a function of Z. And linear variation is something that is the most common to use. So T naught is the temperature at Z equal to 0, that is sea level. And then as you go up, the temperature decreases. So that is true for the first layer of atmosphere. So then you'll have to integrate using this relation. Again, nothing new here. So I will leave it to you to do the integration yourself and see what the pressure function looks like. Okay, so the next discussion here, well, I won't call it the next discussion. We are continuing the discussion. In this case, I mean, there are situations where we have accelerations in the system we are considering. So, for example, the glass example that we just took, it could be the case that the glass actually is accelerating to the right hand side with an acceleration a, and gravity still is acting. Again, our intuition says that if you have liquid in this and you try to accelerate to the right, then the liquid will tend to move up to the left. So we'll have the free surface in this case will look like this. I may have exaggerated that, but it will tend to tilt in such a way so that the liquid on the left hand side will rise. And the intuition is correct in this case. So what we do is we consider the non-inertial frame of the glass, and then we consider the pseudo force. So since the acceleration is to the right hand side, so the pseudo force is on the left hand side. So we will say that the net acceleration will be, uh, well, should I write it this way? So this is my A pseudo, and this is my gravity. So this is my net acceleration. Okay, and I then simply have to, I mean, the relation still is valid. So we have grad P is minus rho. Instead of G, we put an A here, because to calculate the net force, it's the vector sum of the forces because of the pseudo force and the gravity. So this is what we get. And again, grad P is perpendicular to the force. So since the force is acting along the acceleration direction, that is, so the I mean, so this is direction of A, and your pressure isobars or constant pressure lines will be perpendicular to this force. So hence it will be, the fluid will take this angle. So as you increase the acceleration of, I mean, let's say this jar is sitting in a car, and you increase the acceleration of the car, then the angle at which it is slanting will keep becoming steeper and steeper. All right, so the next common example that we have is rotation. And fluids undergo a lot of rotation, and in this case we are considering rigid body rotation. Okay, so if you take a fluid and start rotating it and leave it like that for a very long time, you will see that then the fluid, after a very long time, because initially if you start rotating it, then the layers will start to move with respect to each other because of viscosity. But if you leave that for a very long time, then slowly the fluid will come to a rigid body rotation, that is V equals omega R. So in that case, again, we do the same kind of analysis. So we consider the inertial frame, and then we have to apply a pseudo force. So if there's an anti-clockwise rotation with the angular velocity, with the angular speed omega, then because of the rotation, the fluid is going to take a shape which looks like this. This is my radial coordinate r. So grad P again is minus rho times A. Sorry, I think it's not, there's no minus sign here. I made a mistake. It's rho times A. And this A, in the case that we are considering, so gravity is still acting, remember that. So this A is the vector sum of gravity and the A pseudo. And the pseudo force in this case is the centrifugal force, which is acting radially outwards. So if I was to write this in the vector notation, so this gravity becomes minus g k hat, and the pseudo force it's a radial coordinate system. So this becomes the the magnitude is omega square r for any given distance r from the center, and the direction is r hat. So in circular coordinate systems or cylindrical coordinate systems, r hat points radially outward. So at different distances from the center, you know that the pseudo force is different. It depends on the value of r. Okay, so in this circular coordinate system, my grad p actually is, I'm not telling you the derivation of this, but I'm simply writing this. You may already have done this in some previous course on mathematics or electrodynamics. So in the radial or in the cylindrical coordinate system, this is del p by del r along r hat plus del p by del z along k hat, and then you also have a phi hat component, which actually is a bit different from the Cartesian one, but we won't write that because the right hand side does not have any. So I'll just write plus 0 times uh, phi hat in this case, because the right hand side, because this has to be equal to your sum of gravitational force and centrifugal force, but there's no phi hat component on the right hand side. So if I equate the components of the unit vectors, so we get del p by del r is omega square r, well, with a rho. Did I miss a rho again? No, that's okay. And then del p by del z is minus rho g. Right. So again, I'll let you use your ideas of vector calculus or multivariable function and find that the pressure as a function of r and z will come out to be this. So if I was to find out the constant pressure lines in this case, so all I have to do is I have to write this P equal to constant and find one constant pressure line. So if I put this P equal to constant, so what we get is so that constant has absorbed P naught as well, the constant of integration, and this is what we get. So if I move around the terms, then what we see is that, sorry, what we see is that we get Z, we get a parabola. So we get Z equals to, and then we'll have some constant. So I'll call it A times R square plus B. So everything else, the variables here are Z and R. Everything else is a constant. So I have included that in coefficients A and B. Okay, so this is the constant, one of the constant pressure lines. So if I go back to the figure, then you see that whatever I had drawn earlier was actually correct. It is a parabola. So the constant pressure lines in this case are um, parabolas, or since we're talking about a 3 dimension, they are paraboloids. We call them paraboloids of rotation. Is that clear? Okay, And remember, the pressure is decreasing as you go downwards. So this pressure, if I call it P3, and this call P2 and this P1, then P3 is greater than P2 is greater than P1. So if I was to, now the question for you is, if I was to put a tracer particle, so let us say a very, a neutrally buoyant tracer particle. It could be some small wooden block, which, it will be lighter than water here. So let us say we could make a plastic small bead which had the overall same density as the density of water that we're considering in this case. And if I was to put that here and then leave it, so you know that it's going to, there is going to be some net force on this element, and this element will then, should I say, let us make it wood. Let us make it lesser density than the liquid, because if it's neutrally buoyant, then it will try to stay there. So if this was wood, which had a lesser density than liquid, and if I leave it here, it will tend to rise up. So my question for you is, can you find out the path or the equation of the path that this wooden block will take as it rises up? Okay, so this is an approximate path it will take. In fact, I will tell you what the expression looks like. So it rises in an exponential expression or exponential path. Can you show from this idea, that is from this expression for the constant pressure lines, can you find out the path this wooden block takes as it rises up in the liquid under this pressure field? I'll also mention that see the book for there's a very nice visualization of these tracer particles. So experiments have been performed where where some colored particle was kept, and camera or videography was used, or a long exposure videography was used, to a long exposure photography was used, sorry, to see the path this tracer particle took. So this is experimental visualization of finding out the tracer paths. All right. Any questions on this? Right. So let us keep continuing. I just need a couple of minutes to finish or conclude the discussion on fluid statics. So the next discussion again is nothing new. These are ideas you already know. So if this is the discussion on immersed surfaces. So we analyze immersed surfaces because we're interested in the design of ships or submarines, which are quite common applications of fluid statics. So if we have an immersed surface at an angle, okay, so this angle at which the surface is immersed is theta, and of course this is the side view. So if I was to look at the plan view, then the surface could have an arbitrary shape. So if I was to find the total force acting because of pressure on the top, that is on this surface, so I'll have to find the pressure distribution. Now this is a hydrostatic pressure distribution. So if I was to plot the pressure distribution, it will look something like this. And to find the total force, we'll have to integrate the pressure over the complete surface, which we call gamma here. So a small element is d gamma. So we'll have to integrate the total force acting on all the elements. And if you do that, if you use certain ideas of geometry, you can easily show. I will not do it. If you want to see the details, I will share some material on Moodle. It's also given in the book. So if you do a certain step, so what you will see is the net force. Sorry, the net force can simply be written as the pressure on the center of gravity times the total area. So this plate that you have will have some CG, center of gravity. So all you have to do is the center of gravity somewhere here. So all you have to do is to find the height of the center of gravity. So the pressure of the center of gravity becomes the pressure atmosphere, which is on the top, plus rho times g times h cg, and you multiply that by the total area, and that gives you the total force acting on this plate. I'll definitely I'll strongly recommend that you do these steps yourself to appreciate this conclusion that we have obtained here. And such kind of applications are quite important, because if you're dealing with the surface of a submarine, then you will have to figure out the net force acting on that surface, because if you had to balance that force by applying an opposite force from the inside, then you would want to know how much force you have to apply. Now the other thing is, of course, static conditions also require you to balance the moments. So if you had to, let's say, balance this force and you applied an opposite force on the other side, but that was concentrated on a point, so you had to choose which point to apply that force on, so that this whole plate will not start rotating. So the point at which we will have to apply this to ensure that the moments are balanced is called the center of pressure. And again, it is intuitive, because the pressure distribution is such that it is the pressure is higher near the bottom of the plate as compared to the top. So you can see that if you had to find the net moment because of this force distribution due to pressure, then it will be such that it will be the center of pressure will lie somewhere here. So if I apply an opposite force, which is equal to this F force that we have calculated, which is PCG times gamma, at the center of pressure, then the net moment is 0. And again, I will leave it to you to do that. It's standard mechanics. And if you do that, and if you were to measure the coordinates of the center of pressure from center of gravity, so what I mean is that if your x and y coordinates were measured from center of gravity, so in that case, what you will see is that the y coordinate of center of pressure will be something like this. Okay, there's nothing complicated here. So what you see is that everything is positive because this is integral of y square. So that's going to be positive. So there's a negative sign here. So that means the center of pressure y coordinate is negative. And the way we defined the y coordinate, so the y coordinate was positive above. So that means the center of pressure is somewhere below the center of gravity. Okay, which again makes sense because the pressure distribution is such that it's higher near the bottom side of the plate. All right. Any questions on this? Right. So we'll stop here, and the derivations of these things are I will upload that on Moodle for you to look at yourself. Thank you very much, and I'll see you in the next lecture. If there are any questions, I'm happy to answer them.